Okay, please welcome Bobby Calderwood, the founder of Evident Systems.
Thank you. As Dave said, my name is Bobby Calderwood. My background and why it's kind of relevant for this talk in particular is I come from sort of this weird distributed systems intersects with functional programming kind of background. So I'm very into sort of immutable data and all of those things that come from the functional programming philosophy, but also have been thinking for a long time about how to build distributed systems that have some sort of sane notion of consistency at a point in time. I worked on this database called Datomic at a company called Cognitect, and that was how that database worked. Is you could look up the database value as of any transaction, and you could look at sort of historically see what that database value was. More recently, I've been building financial systems. So I was at Capital One for a number of years, building banking systems in the cloud, and very much relying on events and event streaming to drive those APIs. And about a year and a half ago, I started my own company called Evident Systems to do exactly that, helping banks move mission-critical applications to the cloud. And the way we do that is by building them in this sort of event-driven way. So, early in my company's history, I didn't have any customers, and I was trying to just get started, right? So, a friend of mine had a project that they needed help building, and it was on behalf of this automobile manufacturer. So this is well outside my sort of core specialty a little bit. But they had this problem, and it was a really interesting problem. They were trying things a completely different way. It was this greenfield capability. It had a lot of UI. So this was like this image processing application, super intensive UI stuff, which was fun to build. It's a different talk, but there's some really cool stuff on their JavaScript, ClojureScript front end for doing these image visualizations. But we were uploading these enormous images, and we knew that we would have to do this in this sort of distributed asynchronous way because we need to have workers to, tile and scale and whatever these humongous images that we're uploading. And we suspected that because this was a greenfield capability, it was getting kind of a lot of political light and heat within this automobile manufacturer. Other people would want to see this data eventually. And so just building kind of a queuing system for doing this workers, the work that the workers needed to do wouldn't work because queues are ephemeral, and as soon as you pull a thing off a queue, it's gone, and there's sort of this mutable semantic. We suspected we would need to eventually sort of broadcast what we were doing out to other teams and maybe even replay, in the course of developing the system, replay some of the images into a new machine learning algorithm or into a new computer vision algorithm to try to get better outcomes as we tuned the algorithms we were using. So we decided to build it using this sort of event sourcing technique on streaming data. And we decided to do that on top of Redis, and we implemented it in Clojure and ClojureScript. But why would you do that? That's crazy. Why would you build that way? So the main driver, again, was sort of this asynchronous processing requirement. We had to upload these ginormous images, process them in a pipeline. So there's one step that thumbnailed the image. There was another step that scaled the image. There was another step that tiled the scaled images. So we had this sort of processing pipeline, and we wanted to update the UI proactively as progress was made and as these images became available for viewing and manipulating in the UI. We knew this was a distributed system, and sometimes the UI ends up being sort of the forgotten element of the distributed system, right? We think about distributed systems as being back-end, cool, super hacker stuff. But the UI is every bit as much a participant in this distributed system, and we need to sort of include that participant. We also recognize that in this type of a system, HTTP APIs are not enough. They're great. I love building systems, microservice kind of architected systems, and HTTP APIs play a role in those systems, but they're not sufficient. I've seen companies go down really bad roads of building this crazy balkanized, every object or every entity type gets its own microservice. Oh, we've got the user's microservice and the product's microservice and the order's microservice. It's you're in for some pain there probably. And when you build systems like this, there's also this really creepy non-determinism, right? Where as you're trying to do distributed transactions across multiple microservices, writes are inconsistent, reads are inconsistent. When my caller asks me a question, I have to turn around and ask two friends, and they each have to turn around and ask two friends, like to compose together this answer. There's all kinds of room for inconsistency. If a write comes in and my friend of a friend, but not into the other ones, like now I've served inconsistent data out to my customers. So when you build microservice architectures this way, it ends up kind of looking like this. We have these sort of object-oriented kind of microservices all synchronously chatting HTTP to each other. This is not a great place to be. I do not recommend that you do this. This is AWS from like 2009, I think. I love AWS. Their engineers must be a lot smarter than me because I cannot reason about that. That's, when a change comes into one of those things, what's the new state? How do you reason about what the state is at any point in time? You can't. And not just that I can't because I'm not as smart as AWS's engineers, but it's literally impossible. You've got this non-determinism, so you cannot reason about the system at any point in time here. The other thing that HTTP APIs lack is they face this epistemologic problem, right? If I have to ask you a question to learn what you know, and you have no way of telling me when you learn something new, I have to keep asking you questions, right? So in that scenario I outlined before where, okay, my caller asks me a question, and then I turn around and ask two friends, and they each turn around and ask two friends. What if one of my friends of a friend's learned something new? Couldn't I proactively incorporate that into the answer that I would give to my user, or to my customer, my caller? How do I learn about novelty that someone else is responsible for maintaining, but that I'm interested in and it impacts my work? You can't. You have to keep asking questions. Know anything new yet? Know anything new yet? Anything new? Anything new? So event sourcing is a technique for sort of getting out of this object-oriented, let's chat HTTP synchronously to each other all the time, or any request response protocol, right? I'm not just picking on HTTP. Event sourcing is a way of reasoning about system state that uses a sequence of events as the sort of source of truth. So thinking about a chess game, you can either reason about the chess game by having a game service whose responsibility is to take moves and to mutably maintain a current view of that board. Or you could reason about, and model this in software as, I know what the initial board state is in chess. If I know each move in chess notation, queen to f4 and bishop to, I don't know, I'm not very good at chess, but if I know the initial board state and if I know all the moves, I can trivially compute what the current board state is, but I also have preserved the narrative of how the board came to be in that state, which in many cases is the more important thing, right? For a lot of the business problems we're trying to solve, the narrative is more important than the current state. But we software engineers have gotten into really bad habits because computers and databases and all these constructs that we've built for the last 50 or 60 years mostly just think about current state, right? I'm going to change the value of this memory register from happy to glad. We just think in terms of this sort of mutable semantic of what current state is. Object-oriented programming is pouring concrete all over that problem everywhere you are, right? Everything's just current state, and we mutably change each other's state by calling methods and stuff. This event sourcing sort of architecture for building systems gets out of that. It gets back to an older pattern for keeping records that dates to the beginning of human history, where if I want to write a record, I don't erase an old record and write over the top of it. I just write a new page, or I write a new book. Since the 1400s, we've been keeping financial records this way, where I can't go back and change a ledger entry, because then I go to jail for committing fraud. I add a new ledger entry that reconciles the past ledger entries, right? So most of our record keeping for most of human history has been this sort of accrete-only, add new events and then observe those events to figure out what the current state is. That's how we mostly have done record keeping in human history, except for during the computer age, when disks were expensive and memory's expensive, and so we're just going to mutably destroy everything that we ever do. Event sourcing also facilitates distributed consistency, so breaking outside of just my memory and process space on the single machine. When I have a distributed system and I have a log, an immutable log of events, I can maintain the business narrative of what's going on in my system on this log of events, and then everything else can react to that to update databases and compute current state and invalidate caches and do all the other stuff that we need to do in our systems. But really, the source of truth is this event source. And the other thing that this does sort of organizationally, so this isn't a technology architecture thing, this is like an organizational design thing. Inevitably, when you're building software systems, the way I build software systems, in the context of a big company, one department's building a service that has some internal consumers, and then like the mobile app also calls this thing. And inevitably, when you build a service that's situated this way, somebody somewhere is going to want access to your data. And they don't want your database schema and your current state. They don't care about that. Only you care about that. They want the business narrative of what's happened to your application, because they may have a different way of thinking about that same data, right? If I'm the software application and I maintain my kind of OLTP current state database, somebody somewhere, in the marketing department or in the analytics department or the auditors or somebody wants to know what I'm doing in my app, but they don't really care about my current state. They care about what I have done in the course of operating my service. This comes up all the time in financial services, right? Auditing and compliance, they have to know what we're doing to make sure that we're handling our business in compliance with the regulations. If all my application knows is what it knows right now, and it doesn't know how it came to know those things, how do you audit that system? Splunking application logs or something? That's terrible. Don't do that. Just build your system out of audit logs. Build your system out of this log of business events. That way, you get out of this sort of ETL mess, too, where you're ETLing out of your database and putting it into some analytics database. And it turns out we've lost a lot of the data because of our assumptions and the fingerprints we put all over the data in the OLTP database. And so the analysts now have to go back and try to reconstruct data and fix its fidelity problems and all that. So event sourcing is that sort of way of modeling system state by storing a log of business events. CQRS is a related technique. It goes often together. Greg Young sort of pioneered both of these, really tightly defined both of these characteristics. But CQRS is a very simple idea. It's just separating the action, state mutating things that I do in my system from the perception, where I'm just observing the state of the system. And separating action from perception has a lot of benefits in your systems. Just thinking in terms of inputs and outputs to your system, that's really all CQRS is. And by designing APIs this way, the only way that you can cause change within a particular context is by sending commands to its API. So there's really just one way to introduce change into these systems. And then there's sort of two ways to observe or perceive the state of that system. You can ask queries of the API, or you can listen to its event stream, as I've been describing. So what does this look like? A bounded context, kind of from domain-driven design, that's one business capability, a business process or something that you're modeling. You send commands to the HTTP API. That's where the HTTP API is really useful. You can also ask queries of that same thing. If you just care about current state, great, just ask about current state. The command processor bit, really its only job, first and foremost, is just to emit events. So when it gets a command, it thinks about it. It's like, oh, no, let me look up. Do I know who this user is? You want me to transfer money? Okay, let's look up. Do we know who this account is? Do we know the destination account? Is there enough money in this account to cover the transfer? Okay, if all that's true, great. I will emit an event saying money transferred. As soon as that event hits this event stream, that thing becomes true. And then everything else downstream of that reacts to incorporate that event into its view of truth. So you build these read models, these kind of green things, as a result of these events. So there's a little bit of a different way of thinking about systems. Instead of I get a request from my HTTP API and then I go mutate a database somewhere, the first thing I do in this world is I emit an event, because that's the moment at which it becomes true. And then I process that event to build a read model, or I process that event to send a text message or an email to the user, or whatever. These contexts can listen to each other. So if you have an upstream service, say you've got an orders service, and then you've got like a payment processing service, that payment processing service needs to listen to the order service, because as soon as that order is completed, it needs to know that it's completed so it can be paid for. So instead of that like crazy Death Star diagram, when you build systems this way, this is how I envision them in my head. It's still a high cardinality, right? There's still a lot of things going on, but you can reason about it. This is a river delta in northern Russia. And even though it's still high cardinality and there's still a lot of concerns, I can reason about this. Even my tiny little monkey brain can sort of see that the water comes from the bottom and flows up to the top, and I can reason about, I can drop into any point in the system and understand kind of the direction it's flowing and what things are at any given point in time. So why would I use Redis to do this? Most of the time, frankly, I'm building systems out of Kafka. That's sort of my native stack. That's how I build systems for the most part. But Redis, in the case of my system that we're building for this automobile manufacturer, their ops people didn't know how to run Kafka, and it was felt like driving a nail with a sledgehammer a little bit. I mean, we just had this little tiny bit of data. It wasn't a mission-critical thing. It wasn't high volume. So they already had Redis in the stack. Their ops team was comfortable using it. We were already using it for caching, kind of like in Jan's example. So why not? Well, why not just use Redis? The blog post about streams had just dropped, so we saw streams coming in the future, and we're like, oh, hey, we'll write it using PubSub now, and then we'll use streams when it comes out. An original version of this talk talked about how we actually became contributors to Redis and to Carmine, the Clojure client. Open source works. Sharpen your tools, contribute. It totally works, and I thank the Redis team for incorporating our pull requests. But we moved from a PubSub implementation that we had built into a Redis streams version, and it was a net code reduction. So like after the change, there was less code, and it took us like 2 days, and everything just worked. It was awesome. Anyway, again, different version of this talk. But Redis is already there. It's already in the stack. Your ops people know how to use it. It's battle tested. It just works. And Redis has this awesome new streams primitive. Kafka popularized it. Salvatore saw that and wrote this awesome blog post about, hey, we can do a streams data structure in Redis. Existing data structures almost got there, and there have been a lot of talks about queuing and that sort of thing using Redis. For a lot of those use cases, I think streams also fits, and maybe a better fit in some cases. Sorted sets, lists, PubSub doesn't quite get there in some ways, and the blog post talked more about that. But the bottom line is streams maintain this queryable history and efficiently conveys this ongoing history to interested subscribers. So that's really the value of a streams data structure. And for doing event sourcing, where you care about the history, where the narrative of your system and the business narrative is sort of a first-class concern in your system, streams is a fantastic data structure for that. How do I stream? Xadd, that's how you add things to a stream. You can sort of batch query a stream using xrange and reverse range. And then xread is sort of the other thing. So xadd and xread, sometimes it's all you ever need to build a streaming system. But if you want to go back and query the history and in batches or something, you can use range. And then read group is actually a fan out. It has some really interesting applications, especially for those queuing use cases that we've heard talked about today. But you have to watch out for message ordering, so there's a little caveat there. Why Clojure? I'll spend very little time on this slide. It's great. Clojure and Clojure script. Clojure runs on the server in the Java virtual machine. Clojure script compiles to JavaScript, runs on the client. One language through the stack, and this is my native language, so that's part of the reason we did it this way. But this whole sort of philosophy of event sourcing, immutable data, deriving current state from a sequence of events, this is all very functional programming, so it feels very native in Clojure and ClojureScript. Clojure and ClojureScript also has a great GraphQL server implementation and client implementation. So we used GraphQL for doing this, and GraphQL subscriptions for continuously updating the client. We use React in the front ends, and very seamlessly sort of updated the state of the UI based on stuff that was going on in the rest of the distributed system. So that was a really cool pattern. I was very pleased with how that came together. And Clojure has this awesome client for Redis called Carmine, which is generated from Redis docs, actually, commands.json in the Redis documentation repo. So when we added support for streams to the Carmine client, we actually had to open a pull request against Redis doc to get those commands, the streaming commands, added to Redis doc so that we could regenerate the Carmine client so that we could use it in our app. It's great. It stays really close to Redis semantics. So how would we build a system this way? If we had a coffee shop, say, okay, the first part, yeah, I've built a system before. I know how to build kind of an e-commerce-y thing. Customers put stuff in their cart, and they place the order, and then they come into the shop to pick up and pay for their order. But what about, like, the barista who has to make the drinks? We need some way of conveying the fact that drinks need to be made to this other service that faces the baristas. And then, inevitably, okay, the manager wants to see when inventory levels get low so that they can reorder supplies. With streams, it's easy because each of your bounded contexts is an API. Its first job upon getting a command or a state-changing request is to just write down an event to the stream. It observes its own streams to maintain its current state, but then other contexts can also observe their stream and incorporate their events into my own narrative now. So I can include upstream events into my own event log so that everyone can keep up to date. I have a demo system that works this way, and I was going to show it, but don't have enough time and not set up for it. But in conclusion, this is the way that I love to build systems. I strongly recommend considering building systems this way. Build APIs from an immutable log of business events, not on top of a mutable data model in some RDBMS or even in Redis. And then you can derive your current state and update a whole bunch of Redis data structures as your read models. But the first concern is to keep track of the story of your business. Try Clojure and ClojureScript, and then check out my demo app at this repo. I actually have built the coffee shop, the storefront application, the Barista application, and the inventory management application. Check it out. Thanks.